for T2, which gives you U2, and then T4 and U4. Once you find those U1, U2, U3, U4, you're done essentially. You know, everything else is exactly clear. What is Q23? What is the Q41? The net work is simply the net heat because it's a cycle. Thermal efficiency, you know, I get 54.3, but you know, it's anywhere around there is going to be fine. And then to determine the mean effective pressure, it's simply MRT, you know, you need to first find where the volume V1 is, because MEP is equal to the work divided by the change in volume, okay? The only thing you're given is the compression ratio, because you know how much mass is in the cylinder, and you know the initial state, in other words, the initial temperature and pressure. It's an easy calculation to do, and this was done in the examples in the book anyways, okay? And that's it. So you got your whole full 10 points right there. Problem number 2, something happened that I knew, I was hoping nobody would do, but I think it happened. Remember what the main difference between the diesel cycle and the Otto cycle is that, first of all, it's right at this location. But what are the 4 properties that we need to read? Is it U1, U2, U3, U4?
No.
No, it's not. 2 of them have to be U's,
H's.
and 2 of them have to be H's. That's the main thing. So here, obviously U1, U4, right? But H2 and H3. So those of you who went and had just U1, U2, U3, U4, obviously, that's not correct, you know. But other than that, I think the solution is exactly identical, fixing each of the principal states. The temperature T1 here is known, so you calculate U1, and then because it's a start again of an isentropic process, same story, find what is VR2, interpolate to find the second here. I don't care about U2, I need H2, okay? Which I get here at 904 point something. And then at 3, the temperature is known, so I read the value of H3 immediately. But I pick up the value of VR, and then I compute here what VR4 is. And this calculation was in the example, right? To have to find what is the, somebody asked me, so you didn't give me the cutoff volume, you know? Well, it was not given, but there is a way around it, okay? Which is this way, okay? And once you find those 4 states, then really everything else is, again, very, it's not a problem. Use the ideal gas state to find what is the mass, the heat addition, see here, H1 minus H2, whereas the heat rejected is U4 minus U1. So the U's and then the H's. That's the distinction I wanted to make sure that it was done. And then finding the heat added thermal efficiency is not a problem at all. Last but not least is a cold, it's not an air standard Brayton cycle, but it's a cold air Brayton cycle. That means that specific heats are constant, okay? In this case, you don't even need to look at the tables at all. That's what we said before. You find the change in enthalpies based on the changes in temperatures. That's the whole idea, okay? That doesn't mean that if you do it using the tables, you're not gonna get, you know, you gotta get something slightly different, right? But this is the way it's supposed to be done. I even mentioned what kind of equations you need to be used to find what is a change in enthalpy, right? Now you look at a problem like this, when you set it up, you say, I know this temperature here, T1, I know this temperature T3. All I need to find is really what the temperature here at 2 is and at 4 is, okay? So this problem was really quick, and if you use the 2 equations that I gave you right here, 923 and 924, you can find immediately what T2 is, what T4 is, okay? Once you found those temperatures, you don't need a table, you don't need anything, because to find what is the thermal efficiency, because after all, it's all the H's that you find there. Anytime I encounter, for example, here, Q out is equal to M equal to H4 minus H1, I replace that delta H by Cp delta T, that's all. CP is given, the temperatures you already know, so it's a much quicker solution using this than anything else, okay? No need to look at tables, no need to do anything in this problem. All right, and finding the back work ratio, and then the net power developed, you know, which is the WT and the WC, and that concludes the exam. So,
Are you gonna upload the solutions to Canvas? Like
yeah,
Okay.
yeah, we can do that, yeah. All right, so okay, so last week we started at least talking about you will probably notice very quickly why I don't want to put this in the final, right? But at the same time, I don't want to just overlook the chapter because I kept talking about it from the get-go. It's like how are the thermodynamic tables generated? They include entropy measurements, properties, I should say. They include enthalpy properties. They include internal energies, but we don't have tools, or we don't have entropy meters or enthalpy meters or whatever. Okay. The only thing that we can do if a substance is given to us, we can probably measure its volume, density, pressure, temperature, you know, those types of things. Pressure, temperature, volume are the three key ones, okay? Now, how do you go from pressure, temperature, and volume to internal energy, enthalpy, entropy, and all that kind of stuff? The reason, the way this is done, it's done using math, unfortunately, right? Differential math, that's how people get all these things done. Speaking of differential math, if I have a function here, just as a, for example, f of xy is equal to, well, if I have a function of x and y, a function of two variables, right? And then somebody want to say, for example, what is d of f? A differential of that function. How is that going to be calculated? This is from multivariate calculus. It will involve derivatives because obviously this df will be a function of what? Dx, and it will be a function of dy also. But how? Well, if it is a function of a single variable, right?
Treat the other variable as a constant.
What do we know about df over dx? It's f prime of x, right? Like in here, it's going to be df over dx times dx, right? Plus df over dy times dy. Have you ever seen anything like this before? Probably. If you've taken functions of more than one variable, you probably have done this. Example, I have f of xy is equal to x2 sine y minus, I don't know, y x cubed. Something like this. So what is df in this case? df would be equal to, well, d, remember what this symbol means, right? The little curly thing, what does it represent?
Partial derivative.
Partial derivative. So when you take a partial derivative with respect to x, what do you do with y?
Treat it as a variable. Or a
Treat it as a
constant.
Treat it as a constant. So for example, df here would be what? It would be df over dx, which is 2x sine y minus 3y x squared times dx, right? Because I have to multiply by dx, plus, what is df over dy here? Cosine y, right? Minus x cubed dy. Now, it turns out that most of the stuff that we'll be talking about today in this chapter would be based upon something like this, right? It's differential stuff, okay? So let's start here from the beginning. And the other thing too is that everything is based on pressure, measurements of pressure, temperature, and volume or specific volume, okay? What is the first relationship that you know that involves those three variables?
Ideal gas law.
Ideal gas law, exactly. PV is equal to RT, something like this, right? Now, a lot of work was done in the beginning, before people settled on this type of equation here. There were some equations that preceded it, believe it or not, in the days where we didn't have computers and stuff like that, people were doing some crazy stuff, as you will see. Relationships that were much more complicated than this, okay? Because if you get it more complicated than that, that means this stuff becomes even more complicated, right? So it's a good thing that they settled on just a regular ideal gas law as we know it. So let's start looking at this. So, again, as I indicated, applications of thermodynamic principles requires data for specific internal energy, enthalpy, entropy, and other properties. Everything we have done so far has required us to look into tables to get properties of substances. Okay? So the objective of this chapter is to introduce what we call thermodynamic relations, because that's what the title of this chapter is, that allow internal energy, enthalpy, entropy, and other thermodynamic properties to be evaluated from data that are more readily measured. What is more readily measured? Pressure, temperature, and volume. So the big question here, as we go through, is how do we get these from these? Okay, so let's start with that. It says means are available for determining pressure, temperature, and volume and mass experimentally. That means we can calculate those. However, all these other ones, like enthalpy, entropy, are not readily easily obtained experimentally, so we resort to computational procedure. This is what I'm saying, is that math comes into the rescue and allows us to use the relationships that are here and expand them to figure out what is going on in the enthalpy, internal energy, and entropy. So I'm only going to do 4 sections of this chapter. I'm not going to go the entire one. So we'll talk first about the equations of state. The equations of state kind of go through some equations that have been established before, right? Because everything has to come from this type of relationship. So again, the big question is, what is that relationship? And then we'll go on and talk about important mathematical relations, and then how we develop property relations, and how do we evaluate changes in entropy, internal energy, and enthalpy, which is the goal of this. So starting with the equations of state, we need, so an essential ingredient for calculating this internal energy, enthalpy, and everything else, right, is really an accurate representation of the relationship among pressure, specific volume, and temperature. This is the basis. This is a prerequisite. If you have a good representation of this, then whatever comes out of it is going to be as good as can be, right? If you are starting with the wrong, obviously everything will be wrong. Now, where do we get these PVT relations? Well, these PVT relations can be in the form of graphs, which is really not going to help us very much, or they could be in tables, which again is not really going to help us very much, but analytically is probably better. Why is it better? Because it's easier to work with functions, right? Remember when we talk about continuous functions versus discrete functions, right? Continuous functions, I can take the derivatives, I can evaluate things at any point that I want, whereas discrete, I'm only defined at very discrete points. So, PVT relationship can be expressed in tabular, graphical, or analytical, but analyticals are the convenient ones that we are seeking. That's why people were seeking to find a relationship among pressure, temperature, and volume for a long time. Starting first with what we call the virial equation of state. And this equation was established from principles of statistical mechanics that relates the pressure, volume, and temperature behavior of a gas to the forces due to the to relate the behavior of a gas to the forces between molecules. So people who developed this equation were looking at things at the molecular level and finding out how the molecules actually interact between each other. And they computed the compressibility factor. And incidentally here, what is the compressibility factor for this equation here? C is equal to 1, remember, because it's PV, Z is equal to PV over RT. Okay, so Z as we know it is equal to 1, but we accept it as 1, but in reality it's slightly less than 1, different than 1. So initially we had this equation which shows 1 over B over V, C over V squared, T over T cubed. What does this BT mean? Does it mean it's B times T, or does it mean that it's B has to be a function of T?
Function.
It's a function of T. So not only is this equation highly nonlinear, right? But even these coefficients are themselves functions of temperatures, okay? That's insanity. So in the limiting case where the gas molecules are assumed not to interact in any way, then the second, the third, the fourth term vanish, and then the equation reduces to simply Z equal to 1, which is essentially PV is equal to RT. Okay? Since Z is equal to PV over RT, this gives the ideal gas equation. Okay? But initially, this was how it was done. Now we go on and say, okay, let's look at the two equations of state. Okay? In other words, we still need to figure out what is a relationship between pressure, volume, and temperature, but something that involves two constants instead of just one. Okay? Now, two equations came up. The first one is an improvement over the ideal gas equation, which is PV is equal to RT. This van der Waal came in 1873, and he says, hey, you know, these gas molecules that we are talking about occupy more than the negligibly small volume presumed in the ideal gas equation, and also exert long-term attractive forces on one another. When we're talking about gases, we say that the gas occupies a certain volume, but we are not really looking at the molecules themselves, you know. How much, we say that the molecules occupy a small negligible volume, presumed by the ideal gas equation, and he said that, hey, those molecules actually exert forces between them. We don't need to really know the details about it, except that he just says this. What we are seeking is just a relationship among here, So van der Waals equation comes in and says that P is equal to RT divided by V minus B minus A over B squared. See? To go from here to an ideal gas equation, we should have what? A equal to 0 and B equal to 0. When A equal to 0, B equal to 0, we resort or we finish with the ideal gas equation as we know it. My first equation to you, why do we have bars on top of these? What does this mean? What does this mean? What is the difference between V bar and V? Per mole, exactly. V bar is per, let's say, cubic meters per kilomoles, whereas V is cubic meters per kilogram, okay? So, that's the first equation, the van der Waals equation, and then the constants A and B, we have table 824 that's gonna tell us what those equations are, okay? Table 824 on page, we just need to look at it one time, that way we know that it exists. Table 824 is on page 859. 859, it shows for different substances, for example, for air, the value of A, right? What it is, and what is the value for B. And then for air, for example, A is 1.368, and B is 0.0367, and so forth and so forth, okay? Now, it says introducing the compressibility factor, which is Z is equal to PV over RT, and then some change in variables, in which the reduced temperature is T divided by the critical temperature, and then something that is called the pseudo-reduced specific volume, which is PV over RTC. Then this generalized equation becomes, with this one for van der Waals, then the Z is equal to simply VR prime divided by VR prime minus 1/8 times 27 over 64 over TR VR prime. Again, you don't need to know about the origins of this just yet. And then I'm just going to look at one other equation, because these are two equation states. And this one is the Redlich-Kwong equation. Again, Redlich-Kwong equation, it says two constant equation. The Redlich-Kwong equation considered by many to the best two constant equation of state. By the way, they call it two constant because it involves two constants. And on that same table, by the way, that 824 that we just looked at, you know, for the different substances, it tells you what A is, what B is. You see, the equation is going to look very similar to this, because it says that P is equal to RT divided by V minus B minus A V times V plus B times T to the power of 1/2, okay? So this guy comes in after this, and he says, wow, the equation is probably better this way than it is with the other one, okay? It's still analytically a fine equation, and then he gives us the compressibility factor here, as Z is equal to VR prime over VR prime minus B prime minus A prime So, what does this whole thing mean? All we are doing here is to really trying to figure out what is a good relationship, good functional relationship of a substance that involves pressure, temperature, and volume, okay? The one that we know is the ideal gas equation, right? And here there are two additional candidates, okay? Now this example here, this example just will illustrate will finalize the understanding of it. Come on. Let's take a look at this. Imagine you have a cylindrical container, okay? It contains 4 kilograms of carbon monoxide at a temperature of minus 50 degrees. And this, the container here has an inner diameter of 0.2 meters and a length of 1 meter. So all the information is given to us. The question here is, what is the pressure of this gas that is inside in bars by using, first of all, the generalized compressibility chart, the ideal gas equation of state that we know, PV is equal to RT, the van der Waals equation, or the Redling-Wonk equation. This is a great example. In fact, for this first section, this example kind of summarizes really what we are looking for. We are just looking at a good functional relationship. So we have a gas that is inside a container. We need to figure out what is the pressure. Okay, so how do we do this? First of all, all the specific volumes that we're talking about here are molar, right? Because it's the V bar, right? So the molar specific volume of a gas is required in each part of the solution. So we need to figure this out. First, we need to find how much volume is occupied by the gas, which is the volume of the inside cylinder, which is pi d squared over 4, the cross-sectional area, times the length. So the volume occupied by the carbon monoxide is 0.0314 cubic meters. Okay? Then what? So the molar specific volume is M. Remember, V bar is equal to MV, right? So what is M? It's the molar mass of carbon monoxide. And carbon monoxide has a molar mass of how much? Oxygen is 16, right? And carbon is 12. 16 and 12 is 28. Okay? So 28 gram per mole or 28 kilogram per kilomole times the volume divided by the mass. Okay? Because we have 4 kilograms inside, okay? And here we come up with the V bar, okay? Because P is a function of V bar and is function of the temperature. The temperature is known and V bar is known. So where do we go from here? First of all, we need to use the compressibility chart, right? And the compressibility chart, and we've probably used this in PNGR 255 briefly, one time towards the end. You guys remember? Anyone remembers that figure A1? Kind of looks like this. We used it briefly in the beginning. We're going to be using it again in here. So if you look at this one, at the compressibility chart, first of all, the coordinates are the reduced pressure on the abscissa to find what is, and then you also need what is VR prime. So from table A1 for CO, the critical temperature is 133, the critical pressure is 35, right? So you have to find what the reduced pressure is. The reduced pressure is simply the temperature divided by the TC, which is 1.68. And then VR prime is equal to V bar times PC divided by RTC, right? So we can calculate the pseudo-specific volume, right? Now from that figure, once VR prime is given and TR is given, you can read that and find what is the value of Z, and you find that it's approximately about 0.9. Okay, so if you have your book, you see where the TRs are, kind of the horizontal lines, if you will, are the TRs, right? And then you have the VR primes are the ones that are going across. So when you look at the intersection of both, you find that the Z value is approximately 0.9. If Z is equal to 0.9, because P is equal to ZRT over V, then using the ideal gas, using that, using this chart, the pressure is determined to be 75.9. That's method number one. Now, when you look at the ideal gas equation, well, I know the temperature, I know the specific volume, right? So I just use the equation. I'm gonna check, it's a bit over, but it is over nonetheless, at least it's the same, it's close enough, as they say, 84.4 versus 75.9. Now, let's see what the other two methods are gonna give us. First, to use the van der Waals or the Redley-Kwong, we have to figure out what the constants are, right? So looking at that table A24 that we looked at earlier, right? For CO, the A is equal to this, B is equal to that. When you plug in the values, hey, Redley-Kwong gives me 72.3. That's still less than the 84.4, which is the regular, ideal gas. And the Redley-Kwong equation is gonna, again, you get the two constants and it gives you 75.1. In fact, all the values are pretty much around the mid-70s except the ideal gas equation, which is a little bit over, right? And because that's kind of the simplest one, right? And people have agreed to kind of keep going with it all along. So that concludes that first, at least this first section out of 4, that tells us that we have 3 different kinds of equations. We have PV is equal to RT, ideal gas equation, the van der Waals, and the Redley-Kwong equation that gives us the relationship among the pressure, the volume, and the temperature. Now, what do we do with all this? This is where the math part starts. When we talk about, we always said that we need 2 intensive properties, right, to fix the state, right? So, 2 intensive properties, and then all other intensive properties can be determined as a function of 2 properties. For example, if you know the temperature and volume, what can you get? You get pressure, right? If you have temperature, you have specific volume, you can get the internal energy. And if you know temperature, specific volume, you see all these 2 things in here. You should be able to get pressure, and then from there you can get internal energy, then you can get enthalpy, and so forth and so forth. Now, in general though, if you have, we already mentioned something about this, all these are functions of 2 variables. So we're going to concentrate in this class, this chapter on the function of 2 variables. Why? Because we always need 2 properties to define state. That's why we did not choose 3 or 4, we just chose 2. So if you look at this equation of state, for example, Z is equal to Z of XY, it could be something like P, which is a function of T and V, which is a function of 2 independent variables. Now, if you have then Z, which is equal to Z of XY, right? As I mentioned before, the differential dZ is simply equal to dZ over dx times, of course, with y is equal to constant dx plus dz over dy with x is equal to a constant times dy. Now, as a notation, we call this group here M, and we call this one N. Okay? So based on this, we can say that this is M dy plus N, no, M dx. plus n dy. Where m is dz over dx. Okay? Now, if the coefficients m and n, again, this is from math, if they are continuous, if they have continuous first partial derivatives, and the order in which second partial derivative is taken is immaterial. In other words, if I take the second derivative of m with respect to x and y, that's the same thing as the second derivative of m with respect to dy dx. In other words, the order which you take this guy is really immaterial. As an example, right, if I have just a function z is equal to x cubed y squared plus y, for example, right? If I say that dz over dx is equal to what? That's 3 x squared y squared, right? And then if I take now d squared z, and I take this one and I take its derivative with respect to y, how much do I get? 6 x squared times y. So what did I do here? I took the derivative with respect to x first, then I took it with respect to y. Okay? Now if I take with respect to y first, what do I get? 2x cubed, right? 2x cubed y plus 1, right? And then now if I take the second derivative of z with respect to dx dy, now that I take the derivative with respect to x, what do I get? 6x squared y plus 0. You see, I get the same derivative whether I start with x or start with y. It's a very important one because these functions are very continuous functions, right? There's no break in the function, etc. So if the coefficients m and m have continuous first derivative, then that means here that dm, so that means that d squared, that means that dm over dy is equal to dn over dx. Because if I take the second derivative of this with respect to xy, this could be either the derivative of m with respect to y, or it could be the derivative of n with respect to x. Now we're almost done with this, the foundation of this. Two other relationships among partial derivatives for which applications are found in subsequent questions are sometimes when you take the derivative of x with respect to y at z constant times the derivative of y with respect to z to x at z constant, this is equal to 1. It's almost like the reciprocal, you know, almost can cancel out. And then there is another third relationship, which is dy over dx, dy over dz times dz over dx times dx over dy. And then I think the derivation of this is either in the book or it's available online, is equal to -1. This is the only math that is used to figure out what's going on in thermodynamic tables. Okay? It's based on multi-variable functions, particularly on two variables, because we only need two intensive properties to define states. And here we have z with respect to z and x and y, and we have all the relationships that we need for these relationships to be true. Now you go like, well, you're introducing all these things here, dz over dx and this and that, but you know, how is this going to really help thermodynamics? Well, remember, we have a function P in the first section. What did we say? There is a relationship between P, volume, and temperature, right? So theoretically, what do you have? You have plots. For example, if you have a PV plot, we have seen this before, right? You have a dome, and then you have these types of equations. These are the equations that we're talking about, right? These are the functional forms. Or you could, on a PT diagram, then you have what we call a phase diagram, right? And then you look at this, you go like, what does this mean in here? Well, it's in addition to just being a plot, if I were to talk, for example, of what is dP over dt, dP over dV here, what is it equal to? It's zero, because it's a flat line, so the slope is zero. How is the slope here? Is it positive or negative? It's negative because it's coming down, right? It's coming down, and is it something that I can figure out? Yeah, if I fit a curve through that, I can figure out what that slope is at any point. And it's also negative in here, right? And what is the slope right there at the critical location? That's zero. That's, remember, the inflection point, right? Changes in curvature right at that location, and then everything else is negative, right? And then same thing, so that each line that I have has technically a functional form that's going to work. So mathematical relations in here. It says for the van der Waals equation of state, darn it, I erased it, okay, it's probably somewhere here. Determine an expression for the exact differential dP. Remember that equation, what was it again? P is equal to RT divided by, I think, V minus B. Was it plus or minus?
Minus.
Minus, I think minus A here, right?
No, this is minus B.
Here, minus B,
Minus B, and then minus A,
minus A over
B squared.
B squared, thank you. So this is the this is the van der Waals equation, right?
Right.
And it says, what is dP? So here, P is a function of what? P is a function of T and V. Remember, Z is equal to Z of XY, right? So when you have a function like this, that means that dP is equal to what? It's dP over the first variable, dt plus dP over the second variable, which is V, times at constant temperature times dV. So you're taking the derivative. So what is the derivative of P with respect to T here? That's a no-brainer here, right? It's just this guy, right? So it's R over V bar minus B, okay, times dt. Now, how about this? So if I want to take this with respect to,
Is that V?
that's V bar minus B, right? So, so this is going to be plus, remember 1 over x, the derivative of 1 over x is what? No, that's the integral, right? Minus 1 over x, right? So this is going to be more like minus RT over V minus B squared. That's for this one, for that term, right? And then taking the derivative of that would be, that's almost like a V bar minus 2, right? If I take the derivative of this, would be plus 2a V bar minus 3, something like this. Which is, I think, what you have there, right? So for this term here, and this is obviously going to be dV, and remember the first one is always m, the second one is n, right? M and n. So what is m? M is r over v minus b, and n is rt over oh yeah, I forgot to. It's minus rt over v minus b squared. There you go. Minus rt over v minus b squared plus 2a over v cubed. 2a over v cubed. V minus cubed. Okay, so what do we got? So that's the first question. Show that the mixed, and then here it says show that the mixed second partial derivatives are equal. What is mixed derivative? That means if I take the derivative of this guy with respect to what? To v, it should equal to the derivative of this guy with respect to t. That's really what it is, right? If I take the first derivative of this guy with respect to v, what do I get? Well, again, minus r over v minus b squared. And if I take this with respect to t, hey, minus r over v minus b squared, right? So the mixed derivatives are exactly equal. Okay? So dm over dt, r over v minus b squared, the other one is r minus v squared. And then the rest of it is really just showing that those relationships are true, which is when you start taking the derivatives, you know, you verify that they are actually correct. All right, moving on now to section 3. We've got 2 more, including this one. Now that we have a functional form and we tried it on the Redlich-Kwong equation, right? Our goal, by the way, is to really get in this chapter to something called the Maxwell's equations. Not the electrical Maxwell's equation, by the way. Not the Gauss's law and all that kind of good stuff in electricity. These are Maxwell's equation in thermodynamics. So he had his hand both in electrical stuff and thermal stuff. So in this section, several important property relations are developed, including the expressions known as the Maxwell's relations and the concept of a fundamental thermodynamic function. Thermodynamic function, which we already know about, right? So let's start with the beginning. Remember those TdS equations that we talked about in chapter 6, right? Where does that first equation come from? Which is TdS minus PdV. Where does this equation come from?
Oh,
Was that
first law.
First law, exactly, first law, yeah. I asked it, I think, many times before. It's Q minus W is equal to delta E, or delta Q minus delta W is equal to delta U, or du. And so this is the first TdS equation. Du is equal to ds minus pdv. And obviously, when you replace, when you introduce H, which is equal to what? How is H related to U? What is the relationship between H and U? Enthalpy and internal energy.
PV in there.
You add PV, yeah. So H is equal to U plus PV. When you introduce that, then this TdS equation will become what? TdS plus V dP. Okay? So these we are familiar with, right? Now, a couple of other scientists came in and introduced 2 additional functions. One is called the Helmholtz function. Helmholtz. And then the other one is the Gibbs function, okay? Helmholtz has a psi function, which is nothing more than just taking internal energy which already exists, minus Ts, and gives it its name, It's got every right, right? And Gibbs, he says, well, I'm going to call it G because my name is Gibbs, right? So, and he says, hey, you used U, I'm going to use H minus TS, right? And I'm just going to call it that. And so we have, these are the four, in addition with H equals U plus PV and all that kind of stuff, these are the important property relations, okay? Because the moment here you write something like this, then what is d psi, for example, equal to? Let's not look at there. Just what is d psi here? It's du, right? Minus, what is d of ts? What is d of ts? Remember, we have a product, you just take one, you assume one is constant, right? Let's assume S is constant, dt. Now I take T constant, right? ds, that's what you do. When you take a differential of a product, use the product rule, right? And then you come in and say, that's good. But then you go like, oh, but I have du here. Du minus TDS is what? I can rewrite this as tu minus TDS minus S dt. But then what is du minus TDS? You go like, can I remember something here? Du minus TDS is equal to minus PdV, right? Now suddenly you have a relationship which implies that d psi is equal to minus PdV minus SDT. D psi is equal to minus PdV minus SDT. Before I go any further, if you were to encounter an equation like this, what does it imply that psi is a function of? Well, there is at least V and T, because those are the ones that you are taking the derivatives with respect to. For example, here, H, if you want to write a functional form, H will be a function of S and P. Here, U is equal to a function of S and V, and so forth, right? We do the same thing with G, with the Gibbs function, and then you find that dG is equal to VdP minus SDT, okay? Now, what do we do with all those? In fact, those are the functions that I was mentioning, right? U is a function of SV, just because it's written this form, right? H is equal to function of S of P. Psi is a function of V and T, and obviously the Gibbs function will be a function of P and T. Now we're going to encounter the most important slide of this entire chapter, right? The Maxwell's equation. Now you look at this, you go like, come on, what is this? It's no big deal, really, you know? Why is it no big deal? For this particular reason, let me erase this stuff. And I'm just going to do one example. I think the rest is going to all make sense. Let's, for example, look at the first basic function. Remember what we said? U is equal to a function of S and V. We all know that, right? Where did that come from? Remember, du is equal to TdS minus VdP. Now, because that is the case, what did we say about du is equal to? Well, it's going to be equal to du over ds with v equals constant times ds plus what? Du over dv times at p equals constant, at s equals constant times dv. Right? That's the first differential, right? And remember what we call this guy? M, and we call this guy N. And what did we say? That dm over dv, right? That means and we already said, by the way, that this is equal to, because it's du, right? It's tds minus v minus, what do I have? I've seen this equation so many times. Du is equal minus pdv, yes, that's what I meant to say. Minus pdv. If you compare these two equations right there, right? What is du over ds at v equal constant equal to, by analogy? Isn't it true that this term has to be exactly this? And this guy has to be that? Because we know this equation from the first law, right? And from math, we know that if I take the differential, right, I get this. That means no ambiguity, you know? Maxwell says that for these two to be equal, that means that t has to equal to du over ds at v, right? And that's why you see here, t is equal to du over ds at v. And again, minus p is equal to du over dv at s. You see? Without differential math, there's no way in the world you would get those types of equations. Okay? Now, that's the first two. Now, where do these ones come from? This is from u. Wow, this is from u. And obviously this is from h. Let's just do the h one for fun. H is equal to hs, hsp, right? And then what did we say? That dh was equal to dh over ds at p equals constant ds plus dh over dp at s equals constant times dp. But we already know that dh is equal to tds minus or plus vdp. Okay? So based on these two, what can we conclude? We can conclude that the temperature is equal to what? dH over ds at p is equal to a constant. And what else could we say? That v has to equal to what? dH over dp at s equal to constant. You see how complex they look, but really easy to establish even without looking, right? So you have four equations that are associated, two equations that are associated with each one of these, right? And so t minus p, this one, and then for the psi function and this one is the same. Now, Maxwell's equations, where do these equations come from now? dt minus dv is equal to negative dp minus ds. Remember what we said here before? When you have m and n, what did we say? For the cross derivatives, we said that dm over dv has to equal to what? dn over ds. Okay? But we already said that m is but m is equal to what? It's t. So we can say that dt over dv is equal to, what is n? Is negative p, so minus dp over ds. Okay, which I hope is about this. Okay, dt over dv is equal to negative over dp. Okay, now we don't need to go through each one of them, but just at least you got an idea of where they came from, right? This is from the basic function, this is for the second derivative, the cross derivatives, right? And then some additional relationships is, remember, these additional ones are less. After everything is done, right? This is based on the first derivative, this is on the cross derivatives, and then Maxwell looked and said, hey, by the way, look at this. This is equal to negative P minus pressure, and this one is minus pressure. So what can I conclude? I can conclude that this derivative is equal to this derivative. Does it make sense? Look at this one, for example. du over dv at s, du over dv at s, which is this one, has to equal to d psi over dv at t. Why? Because both of them are equal to negative pressure. Let's take, for example, this one. This is t, this is t. So what is my conclusion? Now my conclusion is that I can conclude that this has to equal to that. In other words, du over ds at p at v has to equal to dh over ds at p, and so forth. You see how we kind of went step by step and got all these relationships, you know? It's a big number of equations, by the way. It's a lot of equations. They are all established like this, but this is the part is that he found a way to kind of go from pressure, temperature, and then kind of march by kind of dancing back and forth between those relationships to get the properties established. I'm not even going to do this one here. So
There must not have been any taverns where those guys lived.
Or maybe there was like way more in the beer than now.
yeah, I don't think they.
How did these guys come up with this stuff? Just trial and error and just.
Yeah, well, they math played a big role in the past, where people were doing differential math by hand because we didn't have computers to do dx and ddas, so they always work with functions, and
Just different thinking back then?
yeah, different thinking, it's very analytical way back when. So the last section of this is, okay, now that we have determined all these Maxwell's relationships, right? It says a fundamental thermodynamic property, remember we had one which involved U. Remember the first TdS equation? The second TdS equation was essentially, they were the only two that we have included today was the Helmholtz function and the Gibbs function, okay? It says the fundamental thermodynamic function provides a complete description of a thermodynamic state. So if you give me this, or that, or that, or that, you have given me essentially a pretty darn good description of the state. Now, in the case of a pure substance with two independent properties, this fundamental can take one of the following forms, as I said, one of them. And this is really the part, this is another important slide in here. It says, in principle, all properties of interest can be determined from a fundamental thermodynamic function by differentiation and combination. Okay? And again, we're not going to be developing any tables or stuff like that. This is just to explain how this is done by looking at one quick example. Imagine you have psi, which is a Helmholtz function, which we said is a function of temperature and specific volume. Let's say we know this. Why? Because we know as we vary the temperature, as we vary the specific volume, we got something, right? Functional form. And we call this the Helmholtz equation. So, now, if I know this function, that means at a particular state I already know the temperature, I know the specific volume, okay? How the heck do I determine pressure? Good question, where do I get pressure from? And then that's when you look at the equations for the you look at this, you go, Helmholtz equation. Remember? Psi is equal to, this is the equation that was given to me, right? So what can I get the pressure from? Okay, I got minus P is equal to or P is equal to minus d psi over dV at constant temperature. Okay, that's that equation 1128, you know, that I mentioned earlier. Okay, so you go like, once you find this, the pressure at this state can be determined from that equation. In other words, P is equal to negative d psi over dV. That means at this point, how much do I know? I know psi, I know T, V, and P. I just calculated P. Then what do I do? Well, I need to find, for example, entropy. You know, and you go like, hey, I'm gonna look back at that table again. What can I get from this table? I can get entropy, just based on S equals minus d psi over dt at V. You see how you're increasing your knowledge of the state, you know, gradually? Okay, so we calculated the pressure by differentiating psi. Similarly, S can be obtained from equation 29 by minus psi over dt. Then you go, okay, what can I do now? Well, I can find U, internal energy. Because remember, psi was defined as U minus Ts, right? I know psi now, I know the temperature, I have just calculated the entropy. That means I can find what U is. Okay? You march from one thing to another by saying that U is equal to psi plus Ts. Then you go, oh, I know now the see, I got the entropy, I got the internal energy. Now we go, oh, I know the pressure and volume, so I can get what? H, which is U plus PV. You see how you kind of construct one step at a time, you know, each of the individual properties. So you calculate U, and the specific enthalpy is calculated using H plus PV. Now, after that, you can get your Gibbs function. The Gibbs function is simply equal to H minus Ts. And you can even get this property, which is the specific heat at constant volume, by taking the derivative of U with respect to T. So it's all done with mathematics and using differential math, okay? Here we go. Almost there. So, with the introduction of the Maxwell's relations, we are now in a position to develop thermodynamic relations that allow changes in entropy, internal energy, enthalpy to be evaluated from measured property data. Okay? So, here now we're trying to apply all this stuff to situations where you have, for example, under the dome or outside the dome, because here you have phase change region, and then you have another single phase, and then here you have two phase, okay? So how do you use those Maxwell's equations in that case to figure out changes? Now, the object of this section is to develop relations for evaluating changes in S, U, and H accompanying a change in phase at fixed temperature and pressure. So principal role is played, there is a Clapeyron equation, this is what we're going to end up with. The Clapeyron equation actually allows you to change what is the enthalpy change between these two states during vaporization, sublimation, or melting at constant temperature, to be evaluated from pressure-specific volume temperature data pertaining to the phase change. Obviously, these are just words. Let's look at them specifically. If you look at those two TDS equations in here, if you want to look at this phase change from saturated liquid on the left-hand side to saturated vapor at fixed temperature from an isothermal phase change, The pressure obviously remains constant, right? So what does this equation reduce to within the dome? Does pressure change as I go from here to here?
No.
So this term disappears, and then you end up with simply dH is equal to TdS. So there is a great relationship between the change in enthalpy and the change in entropy when you're talking about the phase change. Now, the differential equation is dH equals to TdS, and therefore, if you want to find how much you change as you go from here to here, all you need to do is integrate and find that Sg minus Hf, Sg is here, Sf is here, is equal to simply Hg minus Hf divided by T, okay? Now, the change in specific internal energy during the phase change can be determined using the equation H equals U plus PV, okay? Because U because you have H is equal to U plus PV, that means that Hg, right? Well, that means that U is equal to H minus PV, right? That means that Ug, which is right here, this is G, this is F, Ug minus Uf is equal to Hg minus Hf, minus the pressure does not change, so it's the same constant, right? Times Vg, oops, minus Vf, which is equation number 2. So Ug minus Uf is equal to Hg minus Hf minus P Vg minus Vf, and the change in enthalpy, so both of these, Sg minus Hf, Ug minus Uf are functions of what? They are functions of Hg minus Hf, Hg minus Hf, okay? So both of them are functions of the enthalpy change. And you go like, where do I get this enthalpy change from? Because I don't know how to measure it. So the change in specific enthalpy required can be obtained using what we call the Clapeyron equation, okay? Which is dP over dt at saturation is equal to Hg minus Hf divided by T Vg minus Vf, and the next slide actually shows the how this is derived, you know, if you are interested in, and that's the basis for that is really the beginning of Maxwell's equation, which says that ds over dv is equal to dp over dt, and then you move on and figure this out, and that sort of unfortunately concludes this chapter, you know.
Why is that unfortunate?
It's unfortunate because
Spending time with us.
you know, it's you probably now understand why I never include this in any exam,
We appreciate that.
Yeah.
because it's I always figured that it's probably more of a,
I feel like I'm making difference.
yeah, it's
White
like
out.
differential math and this and that, but you know, the only interest I find in it is really it's kind of cool to figure out how they go from functional forms to tables, you know, values that we have nothing
Without
about.
a computer.
Yeah, exactly. So, what remains to be done, which I'm not going to start today, I think I've got so much stuff that I have to do. We've got 2 more weeks to work on an interesting chapter, you know, chapter 12, which we'll talk about kind of HVAC issues, humidity ratio, relative humidity, and all that kind of good stuff. Yeah. And how to read psychrometric charts and so forth. But all right, that's really all we need to know about thermodynamics. Thermodynamics being really the science of energy exchange, right? So it's, in other words, you're looking, what we've been looking at is really substances, which could be air, it could be gases, it could be water, it could be anything. And then somebody gives it to you like this and tells you, okay, how much energy does this guy have? Right? So the only way you can kind of figure this out is by looking at it as a thermodynamic system. Okay, oh, Q minus W. So there is internal energy, there is Q that's crossing, there is W that's crossing, and then once you give me the two intensive properties, I can figure out what's going on. But the most important application of that we've been looking at is really how do we transform heat into work, right? Through vapor power cycles, gas power cycles, and of course the reverse also is kind of important, right? So it is a Q that goes into a W or a W that goes into a Q, you know, and that's really the bulk piece of thermodynamics. And when we get to the heat transfer class, that's when we're going to be looking at first law of thermodynamics. We keep saying that Q minus W is equal to delta E, right? But we really didn't say much about Q. I mean, we just call it Q, and then I keep saying, well, it's a heat exchanger, right? Or heat in by conduction or something like that, but without actually looking at how those calculations are typically done. So that's what we will concentrate on the next part of the class, which is really how do we evaluate just this Q, right? Using the three modes of heat transfer, you know, conduction, convection, which is composed of natural convection, forced convection, and then thermal radiation. And then we'll conclude with heat exchangers. Okay, so sorry it was a short meeting today, but
Apology accepted.
apology accepted. Okay, now I can.